Good morning. Can everyone hear me?
Yeah, we can hear you just fine.
Okay, good. Okay, while we're waiting for people to join, if you haven't already started, create an account. So create a Top Hat account. So go to tophat.com. I'll just put it in the chat. Give me 1 second here. Hold on 1 second, chat. Okay, so you're going to go to tophat.com. And your join code, if you haven't joined already, is going to be 821719. And the attendance code, so every day we get a new attendance code. The join code you only need once. The attendance code for today is 1720.
Professor, I had a question.
Yeah.
About the Slack. I had troubles trying to sign in.
Okay, so I'm going to send out a link for that in a second. Okay, a second here. So I need to go to 323, and I need to invite people. Copy invite link. And need to go back to the chat. Come on, go back to the chat. Okay, so you can use this to join the Slack. And I'm just going to put that in another page as well. All right, let me share my screen. Here are the participants. Okay, somehow we're set up for waiting room, so I'm just letting everybody in before I start to talk. So again, if you haven't done so already, go to tophat.com, create an account. The join code is in the syllabus. I'll also give it to you again. It's 821719. And the attendance code for today is 1720. Okay, so I do ask that you be responsible for recording your attendance. We have very large classes, and it's just there are other things that need to be done at a instructor level. So that's one of the beauty of this, is you can record your own attendance. All right. So let us begin. We've got someone else in the, I'm just going to wait another minute or two. Anyone have any questions for me while I'm admitting people to, I'm going to have to change this setting, but while we're letting people in here. Okay, you will have more questions soon. Okay, so again, I think Top Hat is $30. If anyone has other courses, either with me or with other instructors using Top Hat, It is one Top Hat for the entire semester. And again, we had a join code of 821-21719, and the attendance code, and every day I'll give you an attendance code so you can record your attendance, is 1720. Okay. All right, so let's review the syllabus. So the syllabus is in a Google Drive, and the link to the Google Drive is in the syllabus itself. So it's a little bit of a chicken and the egg, but that's why I also sent it to you yesterday from CUNY First, and also posted it in Blackboard. In general, I don't intend on using Blackboard very much, and I don't intend on emailing you from CUNY First. So we will be using these sort of in-house resources to do our communications, particular Slack, as well as I have an announcements page. Okay, so right now I added an announcement that this is the link you could use to connect to the Slack. All right. If you need to contact me, the best way to contact me is not using email. Reach me on Slack. It's just a very good way of communicating between two people, as well as if I need to then communicate with the class, it's just much more effective than the email, and you'll learn to like it. All right, let's take a look at the time here. So class starts at 10, that's as advertised, but it's going to end 4 minutes later than advertised. And the reason for that is I'm going to just jump to the end of the syllabus for a moment. And we are having our final on Thursday, August 11th, not on Monday, August 15th. I fear everyone will benefit with that extra weekend. Okay, we got some more people joining us here, so I'm just letting them in. Okay, so, but that means we need to make up that class. So there are 94 minutes that are supposed to be for each class in the 6-week summer session. So we're going to take 21 of those minutes and allocate it so you have a almost 2 hours for the final exam. And then that means we need 4 more minutes per class, approximately more like 3.5. And so that's why we're ending 4 minutes later. Okay, so hopefully that's not too much of an imposition, and worth it to not to have that extra long weekend as part of your little break between summer school and your fall semester. Okay, if you need to have an office hour, you can just stay on the Zoom with me afterwards. You can also communicate with Slack, and if we need to schedule something else, we will schedule something else. Okay, just sure. Anyone else joining us? No. Okay, the Zoom info you obviously know already if you're with us on the Zoom today. Slack. So what is Slack? Slack is a platform. It's sort of like not exactly a social media, but it's a chat. It's maybe sort of like a WhatsApp, but it's very well suited for technology. It's very good for posting code and so on. It can integrate with Zoom. It integrates with Google. It's really a wonderful platform, very popular in technological circles. And so the link, the invite link for that is now posted on the chat, and it was also posted in the announcements page. Right, we have a Google Drive. Right now, the Google Drive doesn't have that much. It's got a syllabus, it's got some announcements. It will also be the place that we put lecture slides. It will be the place we put lecture recordings, so you can watch them again if you want, if you missed something, right? So we'll put old exams there so you can practice, right? We talked about Top Hat. This is your join code, and we'll use Top Hat for all kinds of things, not only recording attendance, but also I can ask you review questions. We can have different kinds of things that are available on Top Hat. Also be recording scores there. All right, the next thing is this Zybook. Okay, so we don't have any official print text for this course, but we do have something called a Zybook. This is actually a new Zybook. I've been using Zybooks for quite a number of years, but this is a new Zybook. And it's what's interesting about this particular Zybook is that they took a print book, a regular print book on algorithms, and they converted it into this Zybook. So what is a Zybook? It's a interactive approach to learning. So you don't just read the book, but it gives you a little activity to do to make sure that you paid attention, to make sure you understand the concept, right? So the purpose of the Zybook is not for assessments. It's really to help you learn the material. So when you come to class, you have this perspective, an engaged perspective, so that when you come to class, you're not hearing things for the first time, right? I'm not teaching out of the Zybook, so there'll be things I say in class that are not in the Zybook, things that are in the Zybook that are not going to be mentioned in class, but the two are a sort of a powerful combination. Okay, so you do need to subscribe to that. There is a fee associated with that. You do not need to buy any print textbook. Now, that said, you should be aware of some of the textbooks that are available, or I'm just going to mention a few. So I have a long list of them, which I posted on our Google Drive. Back when I learned data structures and algorithms, these two books were the ones that were popular at that time. But that's not what I wanted to show you. First of all, this Goodrich and Tamassia that you see here. This is the print book that is the basis for the Zybook. Okay, so just so you know where that came from. And I want to mention one or two other books, point them out. Okay, so some of you, maybe you, some of you may have taken algorithms before in another school. And there's a famous book, the Big White Book, very popular with some of the instructors, is this Corman, Liserson, Rivest, and Stein. They just called CLRS for short. So that's a very good book, but it's very theoretical. In other words, it doesn't have code in any particular programming language, but it is a wonderful book. And I want to point your attention to something else here. So look at this. Okay, this book by Schaffer. Okay, you can get that for free in PDF. But the other nice thing about this book is the source code for the algorithms is available in Java and C++. You can download it, all right? So in some cases, you might find that helpful when you're working on an assignment. In some cases, I will actually point out to you where you can download the code. Trust me, there will still be work for you to do, but sometimes we use online code as a starting point for the assignment, right? So those are some reference texts that may be helpful for you. All right, what else can we say? So there are some prerequisites. If you haven't taken these courses, I will usually review material, but it will be a little fast, the review part. So it's good if you have those courses. Okay, here's our online description. All right, so what are some of the goals of this course? Right, so first of all, we want to understand what are some of the big problems in computer science and what are some of the algorithms that can solve them. We want to know how to actually code these algorithms in languages like C++, Java, or Python. We want to know how data structures impact things, right? So data structures can make an algorithm slower, they can make an algorithm faster, and you have to be able to be familiar with the data structures as well as to be able to choose them. Okay, so one of the things we'll do is we might study the same algorithm and look at it and say, okay, what happens if I use this data structure? What happens if I use that data structure? How does it impact things? Right, there's a lot of math in this course, okay? Some of it is math you will have seen elsewhere. Some of it is math that is, sort of specific for analysis of algorithms. One of the things we're also going to try to do is what we call empirical analysis. So the way this course is usually taught is a lot of theory, a lot of math, but we also try to emphasize how does the algorithm perform in practice. And I'll teach you how to graph the algorithms and to put it into nice charts. And we'll do the first assignment together so that you actually get experience with this, and then you'll have a template that you can use for future ones. The language I will be using in most cases is Python. You do not have to use Python. So if you really like Java, that's fine. That's just as good as Python. But just so you know, the language I will be working with in class will generally be Python. If you know Python already, great. And if you don't, you will know Python by the time we're done. So I'm happy to support you with that. And to that end, I recommend that you download and install. It's free. A IDE called PyCharm. If you're a Java programmer, and if you go to Queens College, then you probably have to be somewhat of a Java programmer. You may have used something called IntelliJ. Well, PyCharm is the from the same manufacturer, JetBrains, the IDE for PyCharm. I recommend that you get what's called the Professional Edition. So they're going to encourage you to get the Community Edition, which is free. The Professional Edition is also free with an EDU email. So use your cuny.edu email, or if you're from another school, use your EDU email. Don't use your Gmail account. Don't use your Yahoo account. Don't use your whatever other account. Use your .edu, because when they say you're a student, we're not going to charge you. The Professional Edition has a lot of really nice features in it, some of which are not available in the Community Edition. So that's my recommendation there. Okay, this is synchronous learning, which means we expect people to be on the Zoom. We like you to have your videos enabled, if possible. Creates a sense of community. Every once in a while, we may be asked to watch a video, but that's not the primary means of engagement in this class. All right, let's take a look at the grade composition, because that's what everyone really cares about. They want to pass and they want to do well. So we're going to have three main components of the course. We have the Zybook and Top Hat, right? So that's for the basic learning of the material, basic assessments. Then we have the programming assignments, so we put it into practice. And we have a final exam. So the final exam is in person. It's on the campus of Queens College. It's your responsibility to get through all the paperwork to be able to get access to the campus. And that will be in person on that Thursday, August 11th. In terms of class participation, so there will be people who distinguish themselves in the class, okay? Whether it's answering questions, whether it's being on the Slack and, helping students, figure things out, problems that they encounter. In some cases, it might be someone saying, hey, I wrote a really good summary of the course, that I think I would like to share with the students in the class. So I'm looking for people who are sort of going above and beyond and making it very evident to me and to really everyone. Usually the people know who the students know who these people are, and they're making very clear, hey, I really get this material. And I recognize that when it comes time to submit the grades. Okay, again, we'll have a bunch of programming assignments that can be done in C++, they can be done in Java, they can be done in Python. If you really like another language, that's probably also okay. I once had someone do the programs in JavaScript. And again, we'll code the first one together, maybe even probably tomorrow. So you get a feel for, okay, how do we organize our code? How do we, bring in existing code? We integrate it together. How do we visualize that? So please download that PyCharm. And okay, so this is what we hope to cover. I've taught this course quite a number of times, dating back to 1993. There's some idea of what we can actually cover in a particular lecture, but there may be times where we feel a need to move things around a little bit. Okay, any questions that you have of an administrative nature, things that I wasn't clear, things that I should have said that I didn't get to?
So
sorry to cut you off. For those who are joining, so you should have an account on tophat.com. All right, and the attendance code for today is 1720. So make sure to record your attendance in the Top Hat, because I can't really record it for everybody every time. It's just not efficient. I'm sorry, someone had a question.
Yeah, so I have a question. So is Zybook mandatory?
The Zybook is mandatory, okay? The Zybook is mandatory, particularly in this remote environment. It allows me to see what people are up to. Again, the way to use Zybook is to prepare in advance, all right? So if you look at this, the lecture part of the syllabus, I try to tell you, okay, these are the chapters in the Zybook that are most relevant to what I'm going to be talking about. It's not always a perfect correspondence. And that's why I'm not enforcing that you read a particular chapter before a particular lecture, because they don't match, one-to-one, but that is the intention. The intention is try to read it in advance. You will get more out of the lecture. You'll understand what I'm saying. You'll ask better questions rather than, push it all off. I had a student in a different course who did the entire Zybook the night before the final. I never believed that he was going to do it. He did it, but I don't recommend that. It defeats the purpose. He got his points for it, but it defeats the purpose. So try to, more or less follow this schedule. And once you do it, it's, that part's done. You'll see it highlights it. Again, you only have to do participation activities, and there are 2 sections in each chapter of the Zybook that are, you can look at it, but there's no work to do there, right? So one of them is the exercises. Those are the exercises from the original print book. There's nothing to do there. And then there might be some notes at the end. Again, you can look at it, but you don't have to do any work. All right, so fair question. Any other questions of a administrative nature, course overview nature before we get going with the actual course material?
Another question I had was for the IDE. Can I use like Google Colab for Python, or should I use like an actual IDE?
So I've had students who like the Google Colab. My personal experience with that, I didn't like it. Things like disappear, and I'm not so overwhelmed by it. So I really like PyCharm, but there's again, you don't have to use Python either. You could use Java and whatever IDE. So it's up to you. It's up to you. It's less important than in my 355 class, where there certain things. For example, PyCharm also lets you do nice HTML and CSS and stuff like that. We're not doing that in this class. So it's not as critical, but that's my recommendation.
Thank you.
Okay, fair questions. Any other preliminary questions? You are allowed to code in pairs. I actually encourage it, what they call pair programming or peer programming. I think it's good. You have a little bit of checks and balances, but you do need to have your own copy of the code, and you do need to be able to run the code in your IDE. So you can't say, oh, well, he has the code or she has the code, right? You have to have your copy of the code. So yes, work together, but you got to be able to get it working. So you will need to have some IDE, whether it's PyCharm or IntelliJ or whatever, but you're responsible to run the code yourself, whether it's for me or if we're doing a peer review, whatever it is. All right, any other questions? Okay, so here we go. I'm just going to move this out of the way here. All right, so again, this course is analysis of algorithms. Formally, it's design and analysis of algorithms. Sometimes we'll focus more on the design and sometimes more on the analysis, right? So by design, we have certain paradigms, certain approaches to designing programs. One semester that I taught this course, I used a book by Anani Levin. I think that's probably in the list of references. I can just check that here. So yeah, Anani Levitin, you see that book there? So this was an interesting book. The way it was organized was by design strategy, right? So other books will say, here's a chapter on sorting, and I'm going to teach you 10 sorting algorithms. And here's a chapter on searching. I'm going to teach you 4 searching algorithms. And here's a chapter on graph algorithms. I'm going to teach you a bunch of graph algorithms. But this book says, no, I'm going to organize it by the technique that's used for programming it. So there's a technique called divide and conquer, another technique called greedy algorithms, another technique called dynamic programming. Actually, if you look at this book here, the CLRS book that I mentioned before, this book here, so they do it both ways. In other words, they have chapters on design techniques, but they also have chapters by the problem that they solve, all right? Okay, and then we have the analysis. Analysis, given an algorithm, try to figure out what it does. So you've probably seen this notation before, right? These are 5 notations that we're going to use a lot in this class, right? Which is as a function of n, the input size, how much work does it do, right? So we have f of n, which is the actual function, and then we have O of n, which is like an upper bound. Little o of n is an upper bound. Okay, the difference between them is whether it's inclusive or exclusive, to put it sort of loosely. And then we have omega, right, and little omega, right? So these are lower bounds. All right, there is one notation that's missing here. Is anyone familiar with that? An important asymptotic notation that does not appear in this picture here, which we will talk about a lot in this class. Anybody? And don't bother with the chat. You can just yell out the answer. It's fine.
Theta.
That's correct. And if you don't mind when you yell out, so if you don't mind just saying your name as well, so we get to learn the names here. So who is that? Was that Ilma?
Yes, Professor.
Okay. Okay, good. That is correct. So we have a theta notation. And do you know what the theta notation means? How is it different than the little o, the big omega, and the little omega that you see here? The answer is theta means the same order of magnitude. So the big O and the little o mean upper bound, the omegas mean lower bound, and theta means the same bound. All right, so that's what we're going to talk a lot about this notation in this course. All right. We will also do data structures, all right? So at the beginning of this course, we're going to review some of the data structures from your data structures course. As we go on in the course, we will mention some data structures, more advanced data structures that you probably have not seen before, right? And we're going to say, how do these data structures facilitate the algorithms? How do these data structures change the performance of the algorithm? So that's an important piece of this. So when I took the algorithms at my college, we actually had a joint course. It's called Data Structures and Algorithms. They were tightly coupled. All right, we're going to spend 2 lectures on sorting algorithms. Okay, this screenshot comes from a video, I think it's on YouTube, where they visualize different algorithms in progress, sort of a cool thing. All right, we're going to have 1 lecture later on something called NP completeness, and that relates to one of the most important questions, maybe the most important question in computer science, which is whether P equals NP. Right, we'll talk about this more later on in the course, but P stands for problems that can be solved in polynomial time. NP stands for non-deterministic problems that can be solved non-deterministically in polynomial time. And the question is whether these 2 classes of problems are the same. I think most people believe that they are not, but we don't know. And if you can answer that question, you can get a $1 million prize from something called the Clay Institute, C-L-A-Y Institute. So if you do it in the next 6 weeks, if you solve this problem one way or the other, you'll get $1 million from them, and you'll get an A+ from me, and we'll even exempt you from the final. But that's probably not going to happen. So you might want to think about other strategies for doing well in this course. All right, we have many NP complete problems. One of the most famous of these NP complete problems is something called the traveling salesman problem. It has to do with starting a salesman or saleswoman is starting in one particular city, needs to visit all kinds of cities around the United States or around the world, doesn't really matter, and get back home visiting each place only once. What's the best way to do that? And the interesting thing is all NP complete problems are mutually mutually exchangeable. What do I mean by that? It means if I could solve one, I can actually show how a solution to one is a solution to another. So that's pretty remarkable, considering that there are many different kinds of problems that are in this group called NP-complete, that they would all be related. All right, take a look at this next slide here. So at some point, not today, but in that lecture on NP-completeness, we're going to watch a video. If you want, you can Google it and watch it on your own now. It's called, it's about the halting problem in CS 320. I don't know who here has taken CS 320 already. You probably learn about the halting problem. You'll probably learn a proof that the halting problem is computationally unsolvable. And there's a very nice video about that. So even though our course here, this analysis of algorithms is about solvable problems, you should know that not all problems are solvable. Okay, so let's take a step back. This course is called Analysis of Algorithms. And what do we mean by the word algorithm? So it turns out that the word algorithm goes back well before we had computers. It goes back to the 9th century. It's named after someone whose last name sounded a little bit like algorithm. Not exactly, but over the years it got a little mangled. And the idea was that this gentleman came up with a approach to solving problems. Okay, so again, there are no computers then. He said, here's a problem, right? You need a sequence of steps. And so he really came up with this idea. So that's what we do in this course, right? We don't just, it's not just about writing code, but it's about breaking down a problem, right? So here are some examples of problems, not computational problems per se, right? Baking a cake. So is baking a cake an algorithm? Yeah, right. There are a bunch of steps, right? So first you need to obtain the ingredients, you need to put them into a bowl, you need to stir them, right? So as long as it can be broken down into very concrete steps in a proper order, then that's an algorithm. Okay, can you have an algorithm for putting on your sneakers? Yeah, you can have an algorithm for that. What about painting and color by number? You can say, okay, look at an unfinished part of the paper, look at the number there, go to your collection of magic markers or paint, and get the right color and then apply it, right? You can instruct something to do it. What about driving a car? Is driving a car an algorithm?
Yeah.
Yes, it is, but it's not so simple, right? Because you got to sort of code all those things that we develop in intuition, and then you got to put that into the program for that Tesla or whatever it is. So it can be an algorithm, but in order for it to be an algorithm, you got to really break it all down into very concrete. Okay, so what do we mean when we say break it down? What are the requirements? What makes something an algorithm, right? So there has to be input and output, but notice that the input is 0 or more quantities, and the output is 1 or more quantities. Why is there that difference? So why is output an absolute requirement, but input is sort of optional?
The algorithm could just rather any input and give the exact same thing every single time, but it needs to be some.
Well, that's a different issue, right? The different issue is, does it produce the same thing at exact same time? Oh, I see what you're saying. Well, it could still produce the exact same thing every single time. It wouldn't be a very interesting algorithm, right? But the point is, right, the algorithm is supposed to compute something for us. So if it doesn't compute anything for us, we don't need it, right? If there's no end result, we don't really need it. So that's why there has to be some kind of output, okay? The input, maybe, maybe not, right? So the classic first problem you do in all your programming courses, when you first learn about programming is hello world, right? So there's no input there. The output is hello world. So you don't necessarily always have to have input. Maybe it will create some random data itself. Maybe it doesn't need any data, right? Another important requirement is that it be definitive. In other words, and this comes up a lot in exams. I don't mean I ask you this question. What I mean is people, write stuff on their exam paper and it's not clear, it's not ambiguous. I mean, it is ambiguous. It's like, what do you mean by that, right? Find all the and right, you got to give me steps, right? That, someone who looks at that could say, yeah, I can do that. Okay, it can't be something that's vague. Okay, it's got to be, again, it's got to be effective, which means that it's simple, it's feasible, it's something that we can work with. It needs to be finite. So this one's a little bit less obvious. Okay, it's got to halt. That's the problem with the halting problem, is that the algorithm doesn't halt. It's got to halt. It might halt after a minute, it might halt after an hour, it might halt after a year. That's okay, but it has to eventually halt. So if it doesn't get to the output because it's running infinitely, then that's not considered a valid algorithm. All right, we may bend this a little bit. Okay, when we talk about Monte Carlo and Las Vegas algorithms, we might talk about that. Some slight variations on that. Okay, and then we have correctness. Now, it's assumed that the algorithm ought to be correct, right? That's what we want. Can anyone suggest why we might tolerate an algorithm that's not correct?
Sam, in case it's
And
still
if you,
produces a
again,
result.
if you could identify yourself when you speak, just so I get to learn the names.
This is Sam. If it still produces a result that we want,
Well, do you want it if it's not correct? Why would you want something that's not correct? I'm not saying
thanks.
you're wrong, but just to clarify that, please.
gotcha. I thought you were saying if the algorithm itself is not like ideal or perfect, but still produces a desirable result.
Yeah, so the algorithm might not be perfect, right? But correctness means that it's the right answer. So is there a situation where you might tolerate a wrong answer?
It can be useful for debugging if you want to see what works and doesn't work. The wrong answer is just useful as a correct answer then.
Well, you mean you're getting a wrong answer when you want it to be wrong? Is that what you mean?
Yeah, I mean, you could test to make sure the algorithm shouldn't work.
Okay, well, in that sense, it's sort of, it is correct. You know what I mean? It's like correct. It's the answer that you should be getting. So here are two scenarios to keep in mind, okay? One scenario is where it's not always correct. And we're willing to tolerate some wrong answers because, you know, most of the time it's correct. Okay, so that's the one factor, right? Because to get something that's always correct would be too slow. So we're willing to tolerate if, let's say, 90% of the time it gives us the correct answer and 10% of the time it doesn't. Here's another scenario. Another scenario is where it's too expensive to get the correct answer, so we'll take an approximate answer. So we actually have a whole lecture, and there's also a chapter on this in the Zai book, on approximation algorithms. We say, you know, it's too computationally expensive to get an exact answer. So we're going to settle for something that's approximate. All right, now one of the steps here was that it be definitive. Okay, we always know which way the algorithm is going to go. All right, and that's what happens in this picture on the left. Okay, how many people have taken 320? What? Yeah, a lot of people took 320. Okay, so what does a DFA stand for? DFA stands for a deterministic finite automata. What that means is it's a machine where at each step, at each node, we know what we're going to do in each situation. For example, if I'm in this circle here and I get a 0 as my next piece of input, I'm going to stay in that circle, that state. If I get a 1, I'm going to move to this state. If I'm in this state and I get a 0, I'm going to go over here. If I'm in this state and I get a 1, I'm going to go over here. Right, so it's always very clear where I'm going to go. Look at this picture over here. In this picture over here, if I'm in this state and I get a 0, what do I do? If I'm in that first circle or state and I get a 0, what am I going to do?
Stay in the same state that you already.
I'm going to stay where I am, correct. And what happens if I get a 1?
You can either go to the next state or stay in the same one.
So, right, either I stay in that state or I move on to the next state. So we call that a non-deterministic machine, or in this case, a non-deterministic finite automaton. And again, most of the things we're going to do in this class are deterministic, but we will talk about the concept of non-deterministic machines and how that impacts things. All right, so this is, of course, an analysis of algorithms. And the question is, how do we organize the material, right? We're going to learn a lot of algorithms. How do we organize the algorithms? So there are a lot of ways to do that, right? One way to organize the algorithm is to say what area of computer science, or what area of more generally of life is it used for, right? So a very big topic today is computational biology or bioinformatics, right? So we take computer science, we apply it to biology or to chemistry or physics. We might have data science, we might have computational geometry, we might have the military, right? So we look at an application area, we say, okay, we put all of those into one subject, right? We could also organize it by category, all right? So this is a little different, right? It's saying, I don't care what the application is, but what kind of algorithm is it, right? So we have searching algorithms, sorting algorithms, string algorithms, and that's mostly how we're going to approach this course, right? We're going to have 2 lectures on sorting algorithms, 1 lecture on searching algorithms, one on string algorithms, one on geometry algorithms. But we will do some based on, here we go in the next slide, on design technique, right? So again, this is of course in design and analysis of algorithms, so we're going to learn a lot of different design techniques which can be used to apply to many different algorithms. So let's say divide and conquer, we can use that to solve sorting problems. We can use that to solve searching problems. We can use that in certain graph algorithms, right? So a lot of these techniques can be applied to many different kinds of application areas, as well as to types of algorithms. So we're going to do some of that as well. So become very familiar with these. And you might even want to make a list, each time we do an exhaustive search, make a note of that. Okay, here's another way to break down the space of algorithms, and that is by feasibility. Feasibility means how solvable is it? And what I've done here is I've broken it into 4 categories, okay? The first category are problems that are simple to solve. And when I say simple, I mean, even if you're not a computer scientist, if someone gave you this problem, you would be able to solve it anyway. For example, okay, let's say I have a search, right? So is that hard to do? Say I have a box of papers and I want to find the paper with my name on it. So how do you do that if you're not a computer scientist?
Go through every paper. When you find the one with the name on it, take it out and you're done.
Right, so you go through one paper at a time, you look at it, you see if the name is on there, or you move on, right? So that's a simple problem, or even sorting, right? So if I have a deck of cards and I ask someone who's not a computer scientist, can you sort these cards in increasing order? So they say, no problem. They might ask you, does the ace go before the 2 or after the king? But once you give them that rule, they'll be able to sort. Okay, so that's what I mean by simple problems. Then we have problems that seem hard, but they're actually not so hard once you know how to do it. For example, all right, shortest path problems, right? So if I asked you to find the shortest way to get from point A to point B, you might start trying every single possibility to see which one is the shortest. So there's actually a very simple way to do it using Dijkstra's algorithm. But if no one taught you Dijkstra's algorithm, you're probably not going to come up with it yourself. Okay, we're not all Dijkstra. Dijkstra actually discovered, anyone know how Dijkstra discovered Dijkstra's algorithm? He was on a date with his fiance in a cafe, I think in Amsterdam, and they needed to get to somewhere else. And he wrote out the algorithm on a napkin in the cafe, and he said, oh, we could use this. So they used their maps and his algorithm, and they figured out how to get there. All right, then we have problems that are genuinely hard, meaning it's not just that I don't know how to do it. No one knows how to do it, or we believe that no one knows how to do it, right? So all these NP-complete problems, like the traveling salesman problem, like graph coloring problem, a lot of problems, thousands of these problems that are really hard, meaning we don't know how to do them, and we fear that no one knows how to do them. All right, and then we have problems that are impossible to solve. Okay, so the third bullet are ones that take a long time, but they will eventually come up with an answer. This last category, ones that are impossible to solve, like the Holtig problem from CS320, if you've taken that. All right, so we're going to further divide up the space, right? So let's say it's a problem that is solvable, so we can break it up by how much it uses to solve the problem. And here we break it down into two main categories. We have time complexity and space complexity. Time complexity means how much time does it take, or better yet, how many operations does it take? So how many comparisons, how many data movements, right? How much work does it take? And then we have space. Space is how much storage does it take up? Now, keep in mind that every algorithm takes a certain amount of space, right? The space for the data, okay? When we talk about space complexity, we're not including that because that isn't our fault, right? If it took 1 million bytes to get the data, then it takes 1 million bytes to get the data. What we're talking about when we say space complexity is how much additional space. How much additional space does the algorithm require to do its work? That's what we mean by space complexity. I'd just like to go back to time complexity for a second. And I have a note here, I have a bullet. It's generally not on clock time, but operations or instructions. Why don't we focus on the clock time? When I say clock time, I mean you look at your watch before it starts, you see what time it is, and then when it's done, you see what time it is, and you take the difference and you have the clock time. Why is that not the focus? So here's the thing. What happens if one person is running the algorithm on a supercomputer and the other person's running it on their desktop that's 10 years old? So is that a fair comparison? No, right? What happens if one person's running it in the middle of the day when it's prime time and 100 other people are using the server, and someone else runs it at night when no one's using the server? Is that a fair comparison? The answer is no. So the problem with clock time is the computer may be busy, or it's not an apples to apples comparison, right? So what we like to do, at least in the course, is we focus on operations. How many comparisons did it do? How many data movements did it do? How many swaps did it do? Things like that. All right. Now, that said, when you do your assignments, we will build in an actual clock timing component. Part of it is because it's accurate, and also you're going to be running it on the same computer. Okay, so we're going to compare your result for one algorithm to your result for another algorithm. The assumption is that they're running one after the other, and they will be fairly consistent in terms of what they're measuring. I do recommend if you're running it, maybe downloading a 2-hour movie at the same time is probably not a good idea, because that could obscure your results. Okay. Anyone have any questions so far? Nope. Okay. So we're time complexity. So as mentioned on the previous slide, we have two main measures. One is what we call time complexity, one is space complexity. In this class, we'll mostly focus on time complexity. We'll spend some time talking about space complexity. And we use T of n. See that? T of n, we use T of n to measure time complexity. And what that means is the number of operations. The time doesn't mean, again, how many seconds, but the number of operations it took for an input size of n. Okay. Now, sometimes we break that down further. Okay, so if you look here, it's a little bit small. Hopefully you can see it. There's a subscript there. Can anyone read that subscript? It says T, and then there's a subscript there. What does it say?
TB, TA, and TW.
Okay, good. So the B stands for best case, the A stands for average case, and the W stands for worst case. Okay, and we will, often talk about all three. Sometimes we'll talk about some and not the others. The most important one is usually the worst case, because that gives us an upper bound. It says the algorithm is not going to take more than that, right? Sometimes we like to talk about the average case, because that gives you a good idea of what it actually will take in practice, what you can expect. And then there's the best case. Now, why is the best case not really so helpful to us? And there's sort of two answers to that.
Is it because most times we don't have a best case?
Okay, so first of all, it can be a little deceiving, right? Yeah, 99% of the time you don't get the best case. So what is really going on? What does the average look like? What is the, it's like, I give an exam. So one person gets 100 because they're really smart and they really, but the average was a 50. So you wouldn't say that, the class as a whole knows their material, right? So you want to really know what's really going on here. All right, there's another reason. Okay, it's related to the first reason, and that is you can actually bias an algorithm. So you can build in a lot of functionality into the algorithm to make it have a really good best case. It's going to look for things, for best case scenarios, but it can actually make it worse in the worst case. It can make it worse in the average case. So by focusing on the best case, it's like, to go back to my other analogy, I'll put all my effort into making sure that one student really understands it. And then I'll tell the whole class, hey, look, well, so-and-so got 100 on the exam. So you see, you could do it. But actually, I spent, 4 hours every day teaching that student extra, right? So that student would do really well. But it doesn't, in a sense, it took away from effort I could have done for the class as a whole. All right. So just something to keep in mind, that in most of our algorithms in this course, we will have one input size, but sometimes we have multiple input sizes. For example, let's say we're doing a matrix, right? A matrix like from linear algebra, and we have n rows and m columns. So we have two inputs, right? The number of rows and number of columns. We have a graph. We have a certain number of nodes, a certain number of edges, right? So sometimes there are two inputs, and then the formula for the time complexity should reflect both of those. All right. So what is asymptotic notation? So we already saw it before, right? The little o, the big O, the little omega, the big omega. Someone mentioned the theta, right? Ilma mentioned the theta before, right? So that's called asymptotic notation. Why do we bother with asymptotic notation? Why don't we just say what the function is? And the answer is because we want to know what the behavior is when n is large, right? So let's say we have a sorting algorithm, bubble sort, if you're familiar with bubble sort, right? So bubble sort may actually do pretty well when we, have 10 elements, but it performs really poorly when we have 100 elements or 1,000 elements or 10,000 elements. So what we really want to know when we talk about algorithms, it's not, did it do well in this case, but how does it do when n gets very large? That's what we care about, okay? So we were talking about, performance for large sizes, okay? Because very often the algorithm that is better for the large is not as good for the small and vice versa. So when we choose between algorithms, we're generally focused on the bigger algorithm. Okay, so take a look at this next slide. We got a lot of notation going on here, right? We have big O, little o, big theta, big omega, and little omega. So we're going to define this two ways. First, we're going to define it informally, and then a little bit more formally. Okay, so what does that mean? Big O means it's an upper bound. Okay, our function is less than or equal to the magnitude of g of n, right? This means that the order of magnitude of f of n is less than g of n. In other words, g of n is a bigger size function and f of n is a lower size function. I'm going to skip theta for a second. Okay, big omega means a lower bound. Little omega means a strict lower bound, meaning f of n is strictly bigger than g of n. And then we have theta, which means it's the same order of magnitude, meaning f of n and g of n are the same order. One is n squared, the other is n squared. One is n log n, one is n log n. So they're the same order of magnitude, right? Now, sometimes, ideally, we would like to know exactly what order of magnitude a function is, but we don't always know. So sometimes we need to use the big O or the big omega or one of the other ones. Okay, so now we're going to have a little bit more of a formal definition. Okay, so there's a lot going on in this. Okay, so I try to break it down for you, but we're going to go through it one by one. So the way we read this is as follows. We say f of n is big O of g of n. IFF, what does IFF stand for?
If and only if.
That's correct. If and only if. And what's that backwards E stand for?
For every element.
Right. So it's saying for every n0, I'm sorry. This is not for every. This is there exists, right? There exists a natural number, n0, and a constant, a positive constant. Everyone see that plus sign there, positive real constant. And this is the for all. This is the for every element. So we're saying when n is bigger than n0, f of n is bounded above by multiple of g of n. So let me explain to you what that means. It's saying, I don't know what happens for small n, but when n gets big enough, that's what this is saying. When n gets big enough, and it exceeds some threshold, it's saying that f of n is bounded above by a multiple of g of n. Okay. So we're gonna pursue that a little bit. So take a look at these two functions here. All right, which is the bigger function?
G of n.
G of n.
Okay, are you sure about that?
Yes.
So the answer is, as with many questions asked in this course, the answer is okay. I want everyone here, I want you to plug in 1. Plug in n equals 1 into f of n and plug in n equals 1 into g of n. And you tell me which is bigger. So if I plug in 1, what do I get? In f of n.
1500.
Correct. And if I plug it into g of n, what do I get? 6. Which is bigger?
Obviously.
F of n is bigger. Okay, now I don't actually do the math, but let's say I plugged in n equals 100 into both, which is going to be bigger. See, that's not so simple. Let's say I plugged in n equals 1,000. I think that'll work. So g of n we know is going to be at least 1,000,000, right? If I take 500 times 1,000, get 500,000 plus another 1,000, 501. So g of n is bigger, right? So in general, as n gets large, which one's going to be the bigger one?
G of n.
G of n. All right, but we did see that for smaller n, that wasn't the case, right? So that's where this asymptotic notation comes in. Okay, so we observed that for c equals 400, I guess I did some work to figure out, where that threshold was. I say, I'm sorry, well, for n equals 0, if I use a multiple of c equals 400, then it'll be clear that the multiple of g of n, 400 times the g of n, is bigger than the f of n. Right, let's do another example here. Okay, I have two functions here. So which is the bigger function?
F of n.
F of n. Okay, and that's true, by the way, regardless of the value of n. And yet, we can say that f of n is big O of g of n, and we can say that g of n is big O of f of n, and they're omega of each other. Why? Because what we care about in asymptotic notation, this is maybe not obvious. If you haven't seen this before, this may not be obvious. We care about the order of magnitude. Okay, what does order of magnitude mean? It means the type of function. Anyone know what we call the order of magnitude of this function?
N squared.
It's an n squared function. We have another name for that, but yes, it's n squared. What other name do we have for that kind of function?
Polynomial.
A what?
Polynomial.
You're right. It's a polynomial. By the way, n is also polynomial, just with a degree of 1. What do we call a polynomial with degree 2? We have a special name for that. Begins with a Q.
Quadratic.
Quadratic, correct. Okay, so these are both quadratic. Okay, so what we have now is the formal definition for the other ones. Okay, so there we have a big omega. What's the difference between the definition for the big omega and the big O? one difference. One little difference. Anyone catch it? Want me to go back to the big O for a second? Here was the definition of the O. The definition of the big omega.
Big O is the function is less than or equal to theta.
This is the difference right there. Okay, for the other one, it was less than or equal to C times G of N. And here it's, okay. Here it's greater than or equal to, okay? And then we have theta. Theta means that it's big O and it's big omega, right? It's bounded above and bounded below by the same order of magnitude, which means it's the same, it is the same order of magnitude, all right? Now this, the little o and the little omega are a little tricky. What we're saying here is that G of N cannot be bounded above by F of N, okay? Or saying here is G of N cannot be bounded below by F of N, which means it is bounding the other one from below, right? So if one is not a bound for the other, then the other is a bound for it. So that's what we're saying here. Now that's a little confusing, which is why I'm going to show you another way to deal with this, okay? So this is another way to think of it. You look at the limit, right? So to major in computer science in most colleges, you need to take calculus. But in reality, you don't use so much calculus. It would probably be more important to have probability and statistics. Linear algebra, very important. But there is some calculus that shows up here and there. So here we have a little taste of calculus. And we need the limit of the ratio of the two functions. Does anyone remember what a limit is? From your calculus courses?
As the number gets closer and closer to whatever.
Okay, right. So we look at the behavior of the function as n approaches some value. Now in calculus, you may look at the limit as it approaches 1 or as it approaches 0 or as it approaches whatever. In this course, we're almost always interested in the limit as, I don't know if you can see it, it's very small, and approaches infinity. Why is that our concern in this course and not some of the other kind of limits you may have seen in a calculus course?
Because you want to see how the algorithms like fare when they grow. Like
You want to see how the algorithm performs as n grows very large, right? That's what we care about most in this course, okay? So if we take the limit of this ratio, there are three possibilities. Okay, possibility number one is that it converges. Converges means it's gonna, well, converge to 0 means that the G of N is going to be much larger than the F of N, right? So eventually it's going to become like 0. There's another possibility, F of N is much bigger than the G of N, in which case it's going to diverge to infinity. And third possibility is F of N, G of N grow at the same pace, so they're going to converge to a positive constant. Now, when you do calculus, there are two other kind of limits that could happen. Well, first we have a limit that doesn't exist. That's also possible. But you could have negative infinity, and you could have a negative constant. Why is that not relevant in this course? That's my
That's
question.
the best case.
Well, it's not really so much about best case or worst case.
some of these.
Why is it that, you know, having a negative constant or a negative infinity isn't really relevant in an analysis of algorithms course?
And normally these functions represent how many steps the computer needs to take.
That's what I want to hear. Who was that?
Eliyahu Roth.
Okay, so that is correct, right? What are the F of N and the G of N? These are not abstract functions here, you know, some sine or cosine or whatever. These represent time complexities or space complexities. The time is not going to be a negative time. The space is not going to be a negative space. So we're dealing with things that are positive. I mean, I guess potentially you could have 0, but generally speaking, there's going to be positive numbers, large positive numbers. So you're not going to get a negative without, you know, from two positives don't make a negative. Anyone know the linguist joke? So there's some professor who was giving a talk, I think at Columbia University, and he says two positives never make a negative. There's some, in some languages, two negatives make a positive, but two positives never make a negative. Anyone know the end of the joke? There's a guy in the audience, a very famous linguist, philosopher, and he says, yeah, Okay. All right, so here's our notation, our theta notation. Theta represents all functions that are sort of proportional to that, right? So the first one is functions that are proportional to 1, to a constant. We call that constant time. Okay, you might want to write this down. So algorithm like print hello world, right? Doesn't matter what the input is, it just takes whatever it takes to print hello world. Then we have a logarithmic time. Who can give me an example of an algorithm that takes a logarithmic time? Something you might have seen like in data structures, maybe even before data structures.
Binary search.
That is correct. Very good. Who was that?
Parminder.
Okay, good. Yeah, if you don't mind, everyone, say your names when you talk up, so I get to learn the names. Okay, very good. So that binary search is a logarithmic time algorithm. Next, we have linear time. What's an example of that? We have a lot of examples of that. How about linear search? How about inserting generally worst case search in a binary tree is linear time, a binary search tree is linear time. Depth first search, breadth first search are linear, all right? Then we have n log n. You may have heard the term linear rhythmic, which is a combination of linear and logarithmic. Anyone know an algorithm that's n log n?
Merge sort.
Merge sort, correct, good. Other ones? Heap sort. What about quick sort? Anyone know? Is quick sort n log n?
No, quick sort's n squared.
So I'm glad you said that. So the answer is it depends. Okay, quick sort average case is n log n, and we'll actually prove that in this class. But in the worst case, it is n squared, as you said. Right, then we have quadratic, right? Quadratic is the fancy word for n squared. Algorithms like that, bubble sort, selection sort, insertion sort in the average and worst cases. Quick sort in the worst case. Matrix addition is n squared. So many graph algorithms are n squared. Then we have cubic. Anyone have an example of a algorithm, sort of a straightforward algorithm that is cubic time? Matrix multiplication, right? So if I have two n by n matrices, to multiply them is n cubed. Polynomial time just means anything that's of polynomial form. Then we get into exponential, all right? Things like 2 to the n, or more generally c to the n, right? Things like a truth table, looking at all possibilities, right? Those are exponential time, and those are considered infeasible. In other words, if an algorithm is exponential time, that generally means that it's not practical to be able to use it. We need to look at alternatives. We need to look at approximation algorithms. We need to look at, the different kinds of Monte Carlo algorithm, Las Vegas. Those are kinds of probabilistic algorithms. And then we have n factorial. N factorial is typically when you need to consider all permutations of something. Okay. How are we doing on time? I got some time left. That's good. All right, so here's a slide. It probably needs to be updated. So the last time I checked, but it's probably gone up, is to think about how many Facebook users there are. It's probably more like 3 billion now. It's pretty remarkable. Okay, there are probably more people, more Facebook users than people who have food to eat in this world. Okay, how many people are in the world in total now? 7 billion, something like that. So about a third of more than a third of the world has Facebook. Okay, it's pretty scary. All right. So let's say we wanted to sort all the Facebook users, all 2.5 million of them. So let's take a sorting algorithm that is n squared. What's an example of an n squared sort? We just mentioned it.
Quick sort.
Quick sort in the worst case, but if a more typical n squared would be what?
Bubble sort.
Bubble sort, selection sort, insertion sort, right? Those are the traditional n squared. You are correct, the quick sort in the worst case. All right, and let's assume I pulled this off the internet, but it was a few months ago, so it may have changed too. All our computer does 2.8 gigahertz, right? 2.8 billion operations per second. All right, so how much time do we need? So we take our n and we square it. So that was our n is the size. So 2.4 times 10 to the 9th, right? 2.4 billion, square that. Divide that by the number of operations per second, and that tells us we're going to need about 2 billion seconds to do that. Now, I don't know what that means. We have to translate that. So if I take that number of seconds divided by the seconds in a minute and the minutes in, I'm sorry, the seconds in an hour and the hours in a day and the days in a year, comes out to be 65 years. Okay, so that number of users using an n-squared algorithm with this kind of computer would take 65 years to sort the list of Facebook users. That's pretty scary. Okay, what happens if I use an n log n algorithm? What's an example of an n log n algorithm?
Heap sort, merge sort.
Heap sort, merge sort, quick sort in the average case, right? So now my algorithm, same computer, right? 2.8 gigahertz, right? All of a sudden that goes down to less than a minute, which is obviously a little more manageable than 65 years. By the way, why is even our n log n algorithm unlikely to be able to do this algorithm in a minute? What other thing are we not thinking about?
We're not thinking about the space complexity.
Okay, good. So the space complexity, actually, technically speaking, it's not space complexity either, because I told you the data itself doesn't really count as space complexity. But you are right that it does take up space. So even though technically it's not auxiliary storage, it does take up space. Has anyone ever tried to make an array of, let's say, 3 billion? Try that sometime, you know, Java, Python, C, whatever language you like to program, and try to make an array of 3 billion slots. 3 billion, and they're not even integers, right? These are people, so they're going to be strings. It might even be objects, you know, with user data. So it's not going to happen. It's not going to work. Okay. So how do you sort a big list like that if you can't just load it in? You do need to sort. Anyone know what you do? In other words, you're hashtag, you're gonna have similar issues there. First of all, hash is not really the best way to sort, but you still got to get the data in, right? So hash table is actually less efficient in terms of space than an array. It's better for lookup. That's what hash table is good for. It's good for lookup. So what do we do in this kind of situation where you can't make an array of 3 billion or 2.5 billion things?
Maybe like a merge sort.
Yeah, but not your regular merge sort, not the merge sort you probably learn in data structures. You need what we call a external sort. What's an external sort? It's where I can't load in all the data into memory because it's too big. So I load in pieces at a time. And, you know, I sort that and then I write it back out and then I, you know, read some more in and, you know, gradually I get the whole data sorted, but I can't load it all in. So you are correct, though, that many of the external sorts are actually use a merge paradigm, but it's not the traditional merge sort. So the truth is we're not going to spend, you know, time on that kind of sort, but I just wanted you to be aware. If you look at the Zybook, okay, you can see my Zybook here. So I just wanted to show you something here. So one of the sections in the Zybook is this external memory here, okay? So external memory, more specifically 20.4 external memory sorting. So there are specialized sorts, and you know you could spend several months just talking about those kind. We're not going to really spend much time on that in our class, but you should be aware that there are, you know, you need different strategies for that. Right, what we're going to do with the last several minutes we have is I'm going to introduce you to searching algorithms. And next class, what I'd like you to do, not like you to do, I'm going to for you to do with me together, is we're going to code these search algorithms. So today we're going to look at it from a theoretical perspective. So next time, hopefully you'll have your Python IDE available. but you could work, work with us in Java or your other favorite language if you prefer. I will tell you, we're going to try to do some graphing as well. Okay, so I'm going to teach you how to graph in Python. If you are using another language, you should be familiar with graphing techniques in those languages. So if you're familiar with that, that's great. But otherwise, you may want to stick with the Python, and I'll support you with the Python. Right. So what is a search algorithm? Search algorithm means we have a bunch of data. We're going to ignore the data structure that it's in at the moment, but we have some data, and we need to find a particular thing. Okay, so we might have a list of names, and we want to find Lawrence Titleman in that list. We have a list of numbers, and we want to find where the number 323 appears in that list. Now remember, the list may be ordered, and the list may be unordered, all right? How does having an ordered list help us? Does it help us?
You do a binary search on an ordered list?
All right, so depending on the data, we could use a binary, assuming the data is comparable. We could use a binary search to help us find it more quickly, all right? So that's what I mean by search algorithm. So we're going to talk about some different approaches to searching. Okay, so we're going to start with linear search. So linear search, what does the word linear mean? What's it related to? What other word?
OLN?
Well, you're getting a step out of me, but what other word, what word is the word linear related to?
Like straight line?
Line, correct, right? So it means it's like a line. Why? Because you start at the beginning and you just proceed naturally straight until you either reach the end or you get to what it is that you need. So that's the idea. So typically it's in an array. It could also be in a linked list, but it's some, generally a flat data structure. You start at the beginning until you find it. The convention is that you return the position that it's in. So if you find it in the 4th position, you return a 4. You find it in position 0, which is, available in languages like Python and C and Java. So you return 0. And what happens if it's not there? So it depends on the algorithm, but generally the convention is to return -1. Okay, so -1 means it's not there, and you return an index between 0 and n-1 if it is there. The beauty to linear search is it does not require the data to be sorted. What's the drawback to linear search?
It takes longer?
It generally will take longer, okay? So it could take as much, obviously you could find it in the first try if it's in the 1st position, but worst case, it will take n operations because it's got to go through all of them. And what about in the average?
Isn't it also OLN?
That's correct, right? On average, we would expect it to go halfway through the array, although that's not entirely true, because if the item is unlikely to be in the array, it's actually going to more often have to go through the whole thing to figure out that it's not there. Okay, so it's only, n/2 if it's in the array, but if there's a good chance that it's not in the array, you're going to have to go get to the end to figure out that it's not there, right? But yes, n/2 is also OLN, so it's linear in the average case. Only the best case is going to be in that n family. Okay, so here's some analysis. Here's some analysis, right? So here's our code and here's our analysis. All right, so we have our first recurrence equation of the semester. So anyone know what the word recurrence equation means? Right, here's the term, recurrence equation. We're going to see a lot of these in this class.
Is it recursion?
Well, recursion is a kind of code, right, where the code calls itself. What does a recurrence equation mean? You're on the right track.
The equation uses self.
Equation that references the same function, right? So take a look at this, right? Your t of n references the same t function. What does this mean? All right, what this means is it says when I only have one element in my array, how long does it take to process it? 1, because I have to check that one element and see if my element is there. right? What does this mean? This says, well, if I have if I have n elements, I need one element, one operation rather, to check that first element. And then I need to do the work on the remaining n minus 1 elements. So I'm going to repeat that. Right? It's saying I have to check the one element, that takes one comparison. And then I have to check the remaining n minus 1, whatever time that takes. So we do that a lot in analysis of algorithms, right? We write these what called recurrence equations. You should have seen them in 220 as well, maybe a little bit even in data structures, right? These are equations that are formulated in terms of itself, and we're going to learn some tricks for solving them. Okay, so take a look, and we're going to try to solve this recurrence here. So the first thing we do, and this is not the only way to solve it, but this is one way to solve it. I'm going to move the t of n minus 1 over to the right-hand side. So now I have t of n minus t of n minus 1 equals 1. And then I plug in n minus 1. So if I plug in n minus 1 for n, what do I get? T of n minus 1. If I plug in n minus 1 into n minus 1, I get n minus 1 is n minus 2. And that's still equal to 1. Then I plug in n minus 1 into this, so I get n minus 1, which is n minus 2. I plug in n minus 1 into n minus 2, so I get n minus 1 minus 2 is n minus 3. Okay, so I get a whole bunch of these. All right. And what happens when I add these up? Take all that and I add it up.
You get n?
Well, so on the surface, it looks a little complicated, right? But you're right. If I add up all the right-hand sides, what do I get? How many ones do I have on the right-hand side?
N minus 1 ones?
N minus 1, right? Because I don't have n equations, right? I have starting from 2 up to n. So I have n minus 1 on the right-hand side. Now, what happens when I add up the left-hand sides? Something very interesting happens. Okay, look at this. I have a minus t of n minus 1, and I have a t of n minus 1. They cancel. I have a minus t of n minus 2, and on the next equation, I have a t of n minus 2. Here I have a minus t of n minus 3, and on the next one, I didn't write them all because I don't have enough space. I would have a positive t of n minus 3. They're all going to cancel. The only things that don't cancel is this first one here and the last one there. So I land up with t of n minus t of n, t of 1 equals n minus 1. Now we know what t of 1 is. What's t of 1? You don't remember, I had it on the other slide, right? T of 1 is 1, the work to do with one element. So I replace t of 1 with 1. So I get t of n minus 1 is n minus 1. I add the 1 to both sides, and I get t of n equals n, which means what? It means the work, the number of operations I expect to do in the worst case, this is a worst case scenario, right, is going to be n. Okay, so this is a recurrence. Anyone know what this technique that we just used is? You didn't identify it yet. Give you a hint. What do you use when you want to like look at the stars or the sun or the moon?
Telescope?
Telescope. That's right. And anyone know why we call it a telescope? What happens when you want to put your telescope away? What do you do with your telescope?
Each outer layer covers up the inner layer?
Yeah, they sort of collapse, right, into something much smaller. So that's what's happening here. They cancel each other out. So the technique we call it telescoping, right? So that's an important technique, and we'll use it a number of times in this semester. Okay, so just that was the worst case. The average case is n over 2. That's assuming that the data is in the array, and that makes sense. Why? Because you figure you're going to have to go halfway through the array to find it. The best case, of course, is 1, because it'll just be in the first position. Okay. Now you get to binary search. Okay, do I have a picture here? I don't have a picture here. All right, so what happens in binary search? In binary search, the data is already sorted, and I find the midpoint. I say, what's halfway through the array? And I check. And I say, if it's there in the midpoint, great. I return the midpoint. Okay, By the way, I'm sure most of you have seen this already, but Geeks for Geeks is a great site for code. Have good explanations as well. And very often in the assignments, I'll say, okay, get your code from Geeks for Geeks. There'll still be work to do in terms of getting it running, doing the analysis, the comparisons. So, but it does give you a permissible head start, right? And we say, okay, well, if I didn't find it there, so maybe it's, it's smaller than that. So what do I do here? I look on the the left-hand side of the midpoint. And if it's not there, then I look at the right-hand side of the midpoint, all right? So that's what we're doing over here. Okay, so we're gonna write the recurrence equation for that. And it's this. Okay, why? Because it's saying I need to do one comparison, and then, assuming I don't find it, right? This is a worst case scenario. I have to then do the work on 1/2 the array. That's what this says. This says how much work, if I didn't find it where I was looking, then how much work do I need to do on 1/2 the array? And that's going to be half the size. Now, this is a little bit, this is the standard analysis, but it's a little bit of a mistake. So I want you to go back to the code for a second and take a look and tell me how many comparisons are really being done.
Two comparisons?
2 or maybe even 3, right? So first of all, we're doing a comparison here to check if we're at the end, right? In other words, we don't have anything left, right? Comparing the right index to the left index. Now, technically, that might not be considered a comparison because we're not comparing keys, we're comparing indexes. And keys are more expensive to compare and indexes are less. But in this case, I don't know that there'll be a difference. But you're right, there are 2 comparisons even in the guts of it, right? We're comparing, is it equal? And then we're comparing, is it greater? Or otherwise it's going to be less than, right? So this analysis that I showed you, which is the standard analysis, is not entirely correct. We really should do a 2 here, all right? There is another way to write the code where we don't check for the equality case, okay? We just check for greater than or less than, and we will get the result that way, all right? So that is a variation of binary search that will actually, justify this 1 as opposed to telling us to really write a 2 there. All right. All right, so here we have the expansion method. Okay, so this is another method for calculating these things. So we say, okay, it's 1 plus T of n divided by 2. Well, what is T of n divided by 2? I'm going to write that in here. But what is T of n divided by 2 equal to? Using the same rule.
1 plus T of n over 4.
That is correct. Okay, and then I'm just going to repeat that here so you get the idea here, right? And what is T of n divided by 4? That's just 1 plus T of n divided by 8. So you see what we're doing, keep plugging in the same formula. And then we say to ourselves, well, what's the pattern here? So it's quite obvious that each time I do it further, right, this number is going up by 1. Okay, so we're going to call that K, where K is what? All right, wrong direction. Yeah. Okay, and what about the pattern here? So we keep dividing it by 2, right? So how many times can we divide it by 2 before we're done? We can divide it K times, where K is the log of n. Does everyone know what log means? Log is like the inverse of exponent, right? It's how many times can you raise something, right? So how many times can I multiply 2 by itself? before I get n. That's what this k is, right? So this is saying, okay, well, k is log of 2 of n, and n divided by 2 to the log of 2 of n is 1. All right, so that's the expansion method. Okay, well, we'll do more of these over the course. All right, we're not going to do the domain and range transformation today. And there's our telescoping, right? That was the collapsing we saw before. And we're not going to do the master theorem here. We will do this, though, before we go. So 2 other search techniques. Okay, we'll come back another time to do the math behind it. But so let me ask you this. Has anyone actually used an old-fashioned phone book, you know, the white pages or the yellow pages?
Time ago.
Long time ago, right? Okay, so let's say you wanted to look up my name, Lawrence Titleman, in the New York, you know, white pages. So what would you do? Would you use a linear search? Would you start on page 1 and, you know, keep going until you find Titleman and then you look for Lawrence? Is that what you would do?
No, that'll just take too long.
That will take a long time, right? Okay, would you use a binary search? Would you, you know, would you say, okay, the phone book has 2,000 pages, so we're going to look in page 1,000, figure out if it's there. Otherwise, we're going to look either to the right or to the left. And then let's say it's to the right, because Titleman is probably going to be later than whatever's in the middle. So we'll go to page 1,500, and we're going to look there. Is that what you would do?
Not the most efficient, but it would work, and it wouldn't be.
Well,
terrible.
linear search will also work, and you're right, binary search will work fast, but it's not. That's probably not what you would do. It's not what I would do. So let me tell you what I would do. What I would do is I would say, listen, the name Titleman, T is the 20th letter of the alphabet. So it's approximately 4/5 of the way through the alphabet. So I estimate that my name would be around 4/5 of the way through the phone book. So instead of looking in the middle, I would say Titleman's not going to be in the middle, right? It's going to be towards the end. So I would stick my finger in approximately 4/5 of the way through the phone book, and I would look there. Now, I'm not going to get Titleman on the first shot, right? But I'm going to be in the right ballpark. And then I can use, you know, how far off I am to estimate how far I need to go from there. So that's interpolation search. Interpolation search uses some math to estimate approximately where we would find that. So in terms of numbers, right? Let's say I have a list with numbers, you know, in the range 1 through million, and I'm looking for 1,000. So where would I expect to find 1,000? Roughly, you know, 1,000 over, you know, 1 million, right? It's going to be, you know, that proportion is where I would expect to find it. So that's what interpolation search does. It says, let's guesstimate where we would expect to find it. Okay, just a heads up, and we'll talk about this more tomorrow when we actually code this. There's a little problem here. Okay, so I did take this code from Geeks for Geeks, this double slash. So in Python 2, that double slash worked one way. In Python 3, the double slash works another way, okay? And it's not a way you really want it to work, so we're gonna have to make an adjustment there. But that's not really important right now. What is important right now is you understand the idea. The idea of the interpolation search is to guesstimate approximately where we would expect this item to appear. So we're not arbitrarily always chopping it in half, okay? The interpolation search in the best case, I'm sorry, in the worst case is actually going to be pretty bad. Okay, you can see that it's O of n. That's like linear search. Binary search, worst case is order of n. I'm sorry, is a log of n, worst case. But look at this. The average case is log of n. Anyone know what LG without the word without the O is?
Base 2 log?
Base 2 log, okay? So in computer science, sometimes we don't want to write, especially if you're typing it, LOG subscript 2 is a pain in the neck. So we have a convention LG. But just like, you say ln to represent natural log. So we have a convention LG is log base 2, all right? And we have one more search we're going to mention today. It's a jump search, okay? It's sort of like a linear search, except in linear search, you always jump one thing at a time, right? One unit. You go from position X to position X plus 1. And in jump search, we do different jumps. Okay, so the idea is we can get from one part of the array to another part quickly. And what jump should we use? The recommended jump is of size square root of n, and here's the code for it. But I want to show you something else here. Where's the, you don't have the time complexity here? Have the time complexity there? Okay. Yeah, so it performed pretty well in the average case. Okay, worst case, it's also bad, like interpolation search. Okay, so that wraps us up for today. So just a few closing announcements. Number one, if you haven't signed up for Top Hat, please do so immediately. Okay, if you're not sure if you're staying with the course, you can get the free version. If you do stay with the course, you need to pay the money. I think it's $30 for the actual version. The join code is 821719, and then you need to record your attendance. Okay, so one of the many things we'll use the Top Hat for is for recording attendance. We don't need it just for that, but you do that. And the attendance code for today, I think was what, 1720. Anyone confirm that for me?
Yes.
That worked for me.
Okay, good.
Yes.
All right, so that's one thing you want to do. You want to sign up for Slack, okay? So I sent the link on the chat today. If you didn't catch it, you came late to the class, that's okay. But one of these pages is the announcements page. Okay, so let's see here. Let's say sign up. tophat.com. Let's see, join code, what do we say, 821719, and attendance, or attendance with code 1720. And then I'm also asking you to download Python from python.org and PyCharm from JetBrains.com. Get the, what do we call it, the professional edition, free with your .edu. Okay. All right, so tomorrow we're going to do two things. I'm going to give you a brief background in a review, I should say, of basic data structures. So you should expect that these are all things that you would have seen in your data structures class, things that we'll need until we get to more advanced data structures. And then we're going to code some search algorithms together. Okay, so we're going to do that collectively. So you'll, introduce you to the Python, introduce you to how to structure your code, and also how to visualize it. Okay, so we should be able to do that in the course of our lecture. Okay, I'm going to stay on in case anyone has any questions. Otherwise, you're free to go.
Professor,
Yes.
if we're new to Python, would you suggest that we try to get some kind of intro into it?
I'm going to walk you through it. So I'm assuming you're not new to programming. You're, I'm experienced if you got through data structures that you're, let's say, well-versed in Java, and you'll find it very easy. I'm going to walk you through the program tomorrow. I mean, obviously I would say I'm experienced at this point, but I look things up all the time. So even an experienced programmer looks things up, but I'm going to walk you through your first program, and you'll say, oh, that was easy. Okay. The hard part is not going to be the hard part's not going to be the Python in this course. I'm not saying it's an easy course, but the Python's not going to be the hard part.
Hi, Professor.
Yeah.
This is Hasib. I'm also in your 355 class. I couldn't come to class in the morning. Just wanted to ask, when will you post a recording?
So it takes a while. Some of you may have noticed that when I kept on clicking on the Zoom button on the bottom, it was converting it. So it takes, sometimes it could take a few hours.
Okay.
Before it actually converts to a postable format. And then I post it. So it's usually sometime in the afternoon. Okay, also I have 3 classes. I have to wait for the classes to be over for me even to think about it.
One more question. The top ad is $30, right? Can
I
the
believe so.
$30?
I believe so.
So do you have
And you can use one top hat for
2 classes?
for all, any classes with me, and if anyone else is using it also. Don't forget also to go to the Zybook. So subscribe to Zybook algorithms. Okay. And again, let me just show you what we have here. So this is our Zybook algorithms. So today we did sort of an introduction to algorithms and analysis.
Yeah.
And next time we'll do a review of basic data structures, but what they call basic data structures, they just have some of them. We'll probably, we'll talk a little bit more, maybe, might mention a binary search tree, might mention a heap. Okay, so you want to get started on that. There are a bunch of chapters here. So you want to be doing about 1 a day.
All right, thanks.
Okay. All right, any other questions?
Yeah, Professor. So seems like this class kind of based a lot on the data structure class we have done. So I
That
feels
is
like
correct.
I
Yeah.
feels like I'm kind of lost behind because I didn't do well in data structure class. Are those sorting method and search method you mentioned in the class? Are we supposed to know those like really in details, like, or only we have to know like roughly the ideas?
So, some of the things that we do will be, overlap with things in data structures. Generally, I start from the beginning, but I also do things quickly for the stuff I expect you to have seen before. So we will talk about merge sort, which you probably would have seen in data structures.
So you still like teach it.
But I will do merge sort in the same lecture that I do quick sort, and maybe I do heap sort. So the pace will be faster for that material than it was in data structures, because I'm assuming it's not the first time you're seeing it.
Yeah,
whereas other things, let's say, I don't know, computational geometry, which I wouldn't have expected you to have seen before, we're gonna spend more time on.
Okay. Yeah, because it seems like other people like know those stuff.
Yeah, so we're gonna do around 10 sorting algorithms in 2 lectures.
Wow. Okay, I got it.
Okay. So we do, the data structures is a prerequisite, and we do rely on it. So I do start at the beginning, but we go from 0 to 60 as the expression goes pretty quickly.
Okay, are you gonna sign those sidebooks, Simon? Like, or
so I think most people would prefer not having the pressure of having to get this chapter done on this particular day. So I'm saying you do it on your own schedule, but I will show you this. If you look at this schedule, so these are the topics I expect to cover, and we'll follow this pretty closely. And what I do is I show you approximately which chapter in the Zybook best corresponds with that.
Okay.
So the way, I don't know if you can see, I'm going to bring up my Zybook again. So if you look on the right-hand side of the screen, I'm just going to move move this out of the way. So you see there's an assignments tab.
Yes.
So many professors who use Zybooks, they actually assign. They say you got to read this chapter by this day. And if it's not read, or you read 50, you did 50% of the activity in it, you get 50%. So again, I don't think the students want to be sort of locked into that schedule. So I'm not taking that approach. But just so you know sort of what would be beneficial to cover, I show you so for this one, I have chapter 1 as the introduction, and then there's also chapter 27. So let me just show you what that is. If you go to chapter 27, it's useful mathematical facts, right? So this is just some stuff that if you haven't seen it before, let's say in discrete math or calculus, this is some stuff that will be useful to you.
Okay.
Okay.
And also a question on the slides, if nobody else want to ask the question.
Okay.
Slides 37, you just talked about, it's the recursion expansion method.
Yeah.
I don't know, how does the T part get into one? The right part, the last two line.
You're talking about this?
Yeah. How does
Oh,
the
okay. Because what is 2 to the K? Right there. So 2 to the K equals N. Okay, so what is N divided by 2 to the K equal to?
One.
That's correct, right?
Wait, 2 to the K. Oh, okay. Oh, I see. I got it.
And we know that T of 1 equals 1, right? That's the bit what we call the base case, the
Okay,
initial
I see.
condition. Okay,
Mhm. All right, I
Yeah.
see.
that's
Thank you.
that's the logic. Okay, so we'll do we're going to do more of these recurrence equations here.
Mhm. Yeah, that's it for me. Thank you.
All right, one last call for attendance. So the attendance code for today is 1720. Please enter that in the top hat. All right, anyone else have a question? Otherwise, we're going to go get ready for my next class.
I'm just wondering, is it like feasible to do both the 355 and 323 together? You know, somewhere like this?
It's definitely possible. Many students have done it before. I guess they sort of, fear they'll deal with me twice in the same summer. So it is possible. A 323 is more sort of like 355 is all over the place, right? So in 323, you're going to pick your language that you're comfortable with, whether it's Python, C++, Java. People use different things, but you're going to pick the language that you want to work in, and you're going to probably use that the whole semester. 355 are a lot of different technologies, a lot of things from all over the place. So 323 is more sort of a traditional course. You do something, you build on it, you build on it, you build on it, and you get hopefully you get good at it. 355 is a lot of different pieces. But that said, people have done, and very often the people who do well in one are the ones who do well in the other. So. I don't know if did that answer your question?
Yeah. I was going to do both, but I ended up dropping it. But I don't know if I should try to get into
I mean,
it.
it also depends on what else you're doing. So if you're working, 40 hours a week at a summer job, and you need to do your job, so you're probably not going to have so much time to do your work. If you're sitting at home and you have a few hours a day to devote to each class, then there's no reason you shouldn't do it. It really depends on, what other responsibilities you have.
Yeah, it looks like the chapters are pretty big for this class, so I feel like it might take a while to get through them, especially if I'm trying to fully understand everything. So that's kind of what worries me.
Yeah, the side books, they're not that bad. I mean, it's, you have to do a few activities. You'll also find, you can click your way through things. A lot of them, let's say it's a multiple choice question, so so that's not the intention, but sometimes you can. The important thing is to make sure you understand the lecture, so that that's the goal. The goal of the ZyBook is to provide you the background information, so that you can come to the lecture better informed, and you'll get more out of the lecture.
see. Thank you.
Okay.
Is Professor going to be on campus at all?
I will be on campus for the final exam, so that's my one visit to campus. So are you
So
asking?
office hours would be,
So
like,
generally, you know,
virtual?
the first stop is, you know, try to talk to me at the end of class before the next class starts. You can also reach out on Slack. And, you know, we get some good communication going on there. And if you need to schedule an appointment, something that really can't be achieved on Slack or let's say on the Zoom here, you know, we can schedule a separate Zoom meeting. So I'm here for you.
Sounds good, thank
I'm
you.
here for everyone in the class.
Thank you.